Hello everyone, this is Spencer Snolling from Hydromantis, and I'm glad to welcome you to our usual Thursday afternoon webinar that we're doing this month, where we're going to be going back to basics, as we call it. This webinar is designed for people who are new to GPSX and possibly new to modeling wastewater treatment plants. It will not assume that you know anything at all about modeling, and I'm going to sort of introduce a few ideas about why modeling is important and how it can benefit you, and then I'm going to go through some very basic demonstrations of how to put a model together in our software and get some perform a simulation and get some results out of that. So my name is Spencer Snolling. I'm Vice President of Product Development here at Hydromantis. And my plan for today is to as I mentioned, discuss a little bit about why modeling is a useful tool, just to give you a few examples of how people currently use GPSX and how models can be used in the consulting industry and can be valuable tools for your clients. I'm going to just very briefly, a few slides, discuss the activated sludge model basics, talk a little bit about the development of these models, what's in them, where the equations come from, and so on. And then discuss also how to set up a model in GPSX, and I'm going to run a desktop demonstration of how to build a model from scratch and run some simulations and so on. We'll learn how to do that. We'll learn how to get some output out of GPSX, and then of course I'll answer any questions that you might have at the end of the webinar. So you may have seen that there is a questions box in your GoToWebinar dashboard, so please feel free to type any questions that you have in that box, and I'll be able to see them here. And what I usually do is collect those up, and then I'll run through the answers to the questions at the end of the webinar. Okay, so why is it that people want to use modeling? How is it a useful tool for me when I'm doing wastewater engineering work? And most of the time, the answer to that question is that the model it can stand in for a real system and allow you to do testing and comparisons and analysis and otherwise have something that you can perform some analysis on without having to do it on the real plant. The reason why that's useful, of course, is because most of the time that's cheaper than modifying the actual real system. It might not even be feasible, of course, most of the time. It's easier than carrying out testing on the existing systems. It's often used as sort of a preliminary step before you get to doing actual field testing because it is sort of a nice, easy way to sort of screen out a number of different alternatives in a very cost-effective way. Obviously, it's risk-free. You can take a plant and have a model of that plant and do whatever you want to it, and it can fail spectacularly. But of course, there's no risk, of course, to anybody coming by and fining you for effluent excursions. And of course, the answer is that you get your results quickly. That's one of the most important things. Many places, if you were to change your wastage rate, for example, you would probably have to wait at least 2 weeks to find out where that new mixed liquor was going to equilibrate at. Whereas, of course, in models, you get the answers pretty much instantaneously. So modeling is a useful tool because it allows you to do a lot of analysis in a very easy, straightforward way and get the results back pretty much instantaneously. So how does it work? What is the normal way that we go about doing this type of work? So the first step, of course, is to create a model. And you're going to need a lot of data to be able to put that together. Of course, you need to know the plant tank sizes and how they're hooked together and how much is being recycled, how much is being wasted, and one of the most important things to know is what is the characterization of the influent that's coming in. So some sampling usually is required, and you'll have to drag out some drawings and measure surface areas and so on and get a lot of that information. So you put that into the software, and then you then take a look at the performance of that plant, and you select a month or so of a good sort of typical performance, and then you make tweaks to the parameters in your model in order to calibrate it to some known performance. It's usually this calibration step that actually takes the time during model setup. Setting up the model and creating it in GPSX is fairly straightforward. Taking the time to go through your data and find a good time period to use for your calibration and getting that data into GPSX actually iteratively going through the process of making parameter changes to calibrate that model. That's usually where the actual major effort is, and where, you know, a lot of the knowledge that and experience that comes with doing modeling comes out in that step. So once you've done that, you now have a model that has been calibrated to you know, actual real-life data. And that's where you now have a valuable tool in your hands that you can do a number of things with. So what often happens is that we start by doing a base case. That is sort of our typical performance of the plant under our sort of no changes scenario, and this is usually the situation that you've calibrated the plant to. And then you can run any other number of different scenarios. They might be what happens if the influent is different? What happens if we have a higher influent load? What do we have if it's warmer? What do we do if we have a couple of clarifiers out of service? You know, literally the list is endless. You could run a number of different scenarios and then, of course, compare those answers together. That gives you the ability to sort of say, here's where we are right now, and what if we operated that plant differently, or what if it was actually designed differently? And I want to be able to compare and see if that makes things better or worse, or how much new capacity can I have. And literally the amount of different types of scenarios that you can run under GPSX where you change some of the input parameters is quite endless, and I'm going to run through some examples of these a little bit later on. Okay, so now we're sort of looking under the hood here, so to speak, to get a feeling for you know, what is in GPSX, what is in these activated sludge models that we use. Well, first of all, I can tell you that all of the equations that we use in GPSX total something in the neighborhood of about 10,000, something in that neighborhood for a typical plant. By that I mean, of course, all of the state variables that are going to be solved for, all of the concentrations of all the forms of COD and nitrogen and phosphorus, and all of the other parameters that are there, the pH, and all the calculations for the gas transfer and so on, make for quite a long list of variables that we're calculating and solving for when we run a typical activated sludge model like the one that I'm showing here. So the way we do it, just to keep things organized and make it in a way that can be understandable, is we do it on a unit process basis. So that means that we have an influent that's been characterized, and then some flow stream goes into the next unit downstream, and we solve that unit, and then it goes down into the one beyond that, and so forth and so on. And sometimes there are recycles that come back to the head of the plant and so on, and that makes it actually quite a bit more mathematically challenging. However, we have the ability to sort of iterate through answers and converge to a final answer that makes sense throughout the treatment plan. So the content of the models, the part that makes you know, this thing that we do valuable, is that each one of these unit processes has a number of submodels already built into it, and these are going to cover off things like the hydraulics. And by hydraulics, I don't mean energy grade lines. I mean just sort of controlling about how much flow goes through this particular system. This is a plug flow tank, so it's pretty straightforward. All the flow moves down. But for something like an SBR, you have to keep track of the amount of feed flow coming in and pumping the tank down and decanting and so on. So that can be somewhat challenging. There's always, for the activated sludge units, an aeration model. So that's a gas transfer model that's bringing oxygen into that system. And if you've used GPSX, you know, of course, there's lots of detail there, too, as well, in terms of, for diffused air systems, what kind of diffusers do you have and what the depth is, and calculating oxygen transfer efficiencies and so on. Then we get to the biological model. And it's probably the most detailed part of any activated sludge unit. We have models of different levels of complexity, right from the very first ones that were published back in the 80s, ASM1 and so on, up to and including the ones that we have developed here at Hydromantis, our in-house models, Mantis and Mantis 2, that can be used to do modeling of all sorts of BNR systems. And so there's dozens and dozens of equations that describe the transformation of COD and nitrogen and phosphorus and other components in there to be able to understand how the growth of the bacteria happens. We have a lot of kinetic equations with saturation terms and so on that basically describe how these bacteria are going to grow under different circumstances, whether it be anaerobic or anoxic and so on. And then stoichiometrically, we can figure out how much of each of these types of COD has been converted into some other form. So there's a lot of detail there. The more complex models divide their COD into more finely chopped up versions of COD. We have soluble inert material, readily biodegradable substrates, fermentable substrate, and so on and so on. So as you go to more complex models, the fidelity of how we keep track of things becomes more complex. However, no matter what level of complexity we're using, we're always doing mass balances on all of those things. Mass balance on each of the individual different types of COD, a mass balance on all the types of nitrogen there, the ammonia, nitrite, nitrate, and so on, and all the way through the whole plant. Okay, so on to the more complex models have gas transfer. So for parts of GPSX where we have the more advanced libraries, and we're keeping track of things like the generation of methane, our other, our carbon footprint, and greenhouse gas library has even more things that are included in those calculations. Those are all parts of the model that are there so that you can get an estimate of the loss of gases to the atmosphere and so on. We have a pH model in our Mantis 2 model where we now have to keep track of, in addition to everything I've already said, on top of that, we're now keeping track of things like calcium and magnesium and potassium and all the other ions, cations and anions that are there that become part of the electroneutrality balance. And so, they're sort of building upon levels of complexity here. And in places where we have the ability to keep track of all of those elemental anions, we can also start to do things with the precipitation. So we're including physical models here, hydraulic models, we have gas transfer models, chemical models, and they all are there together and solved simultaneously. So this is a very long-winded way of saying we have a lot of stuff buried into that one tank model that you see when you put it down on the screen in GPSX. So I mentioned earlier that our biological models, the ASM1 model that was developed back in the mid-'80s is sort of the structure that all of the models that we use at Hydromantis, and pretty much all of the models in our industry, are developed upon. That sort of growth and death, growth and decay model with first-order growth rate terms with some saturation terms on them. As time went on, ASM2 and 2D and ASM3 and so forth and other models have been developed, and they've all sort of taken the same approach. ASM1, as you probably know, is only carbon and nitrogen, whereas ASM2D added phosphorus into the mix, and then some of the more complex models have added more onto that as we have gone along in time. So that allows us to sort of get a prediction of how much mixed liquor am I going to have, how much sludge production do I have, all of those kinds of important things that are there and are relevant questions that you would like to be able to ask of the model. So I have a slide here that I think tries to summarize in many ways the most important or the most common uses of GPSX. What are people doing with this software right now? What kind of questions are they asking of the model? Well, at the design level, I've certainly seen a number of people using it to sort of compare various process designs and operating strategies even before the plant has already been built. So after design has been put together via whatever normal method that a company would use to design a wastewater treatment plant, that design can then be put into GPSX as a model and then run and basically stress test that and beta test that design in the modeling software. And certainly there are a lot of people using it for that feature. However, I would say probably even more common than that would be using models to verify existing plant capacity. This is particularly used in places where somebody is modeling a wastewater treatment plant for the first time, where a plant has been running, it may be running quite well now, it may have lots of capacity now, but the people who are operating that plant want to know how much capacity do I have left, and a model is an excellent way to figure that out. You can, as I mentioned before, construct a model, use some of the current historical data to get a calibration of that model, and then you just start ramping up the influent loading to that plant, and you see how far you can increase that loading until the plant fails. And then that way you can see a rough idea of what capacity is left in that plant. And when you get to that failure point, you can actually look into the details of how it failed. Look, where is that bottleneck? Is it because I don't have enough oxygen? Is it because I don't have enough clarifier capacity? Am I running out of digester capacity? that sort of thing. It allows you to sort of not just understand that the plant will fail at a certain flow rate, but actually understand which part of the plant is the one where the weakest link is. So in various other ways, you can do the same kind of question. You can say, what is going to happen in the future if we have, say, a much weaker influent, or we have a much stronger influent with the same flow rate, or what is going to happen in the future if we have a change in what our effluent quality needs to be? Are we still going to be able to match that given the plant that we have right now? Now, certainly, once those sort of initial steps and analysis have been done with the models, you can look at identifying cost-saving strategies as part of a way to analyze the performance of that plant. I have quite a lot of people who are new to modeling who come to Hydromantis and say, you know, our plant is actually running quite fine. We're not worried about you know, being in danger of not meeting our effluent requirements. However, we want to get this exact same performance we have now, but I want to do it more cheaply. You know, where is it that I have some opportunities in my plant to be able to save some money by turning down some pumps somewhere, or spending a little bit less on chemicals, you know, dosing a little less somewhere. And the model is an excellent tool to be able to do that. You can identify any number of different places in the model where I can recycle less. I could, you know, reduce my airflow. I could reduce my chemical dosage. And what the model will allow you to do is evaluate directly what is the impact of doing that. You know, how much is my my effluent quality going to decrease if I dial back my aeration a little bit? We get quite a bit of interest coming to us by people who want to use the model to study the impact of retrofitting an existing plant with a new technology. So, for example, probably the most common version of that we get is I have a plant that's running right now, conventional activated sludge. We're thinking about adding IFAS plastic media, and I want to know how much more capacity that will bring to my plant. And that's certainly something you can do in GPSX by putting that right in there, having those two plants running side by side so that you can compare the new and the old and see what kind of difference you get. And certainly I would say this is a bit more of an advanced feature, but it's something that we've seen quite a bit in the last few years now, is using modeling in support of regulatory decision-making and regulatory analysis. It says here, using it forensically. That's certainly something that I've been involved with a couple of projects where a plant had some sort of issue, there was some deviation of the performance, and actions were taken, and then the regulator wanted to know, or felt that that was maybe not the appropriate action to have been taken at that plant, and the model was used after the fact to go back and say, well, what if we had done something differently? Would that have actually saved the day? And the model has been used to show either whatever action they would have taken, it didn't matter, or there was actually a better action that could have been taken. So it's kind of a way of going back and replaying history and trying a different idea of what would have happened at that time. So anyway, there's a number of ideas of things that people are using GPSX for. Okay. So what I'm going to do now is I'm going to hop over to my desktop here, and I'm going to do what is essentially tutorial 1. If you have a GPSX license and you are using our tutorials, you can, the very first step is just to teach you how to put together a very simple, straightforward activated sludge plant, and I'm going to go through that process right now. So I'm going to give you a little quick tour of the software if you've never seen it before we get started here. And this is a big white drawing board here on the right. This is, of course, the area where you are going to draw the schematic of your wastewater treatment plant. And the objects that you need to be able to do that are all found here on the left-hand side. So we've grouped them all together in sort of units of similar type. There's a number of different types of influent here. I'm going to start out by grabbing just our traditional, straightforward, continuous wastewater influent. So that's the amount of flow coming into the plant there. We have a number of splitters and combiners that can be used to move the flow around the plant, and you'll probably need a few of these in most cases. Some preliminary treatment icons here that are used for things like pumping stations and equalization and chemical dosage for doing things like a ferric addition for doing phosphorus removal and so on. And then we get into our large library of suspended growth processes. So these are your activated sludge units. And we have completely mixed tanks. We have plug flow tanks of various kinds, high purity oxygen, MBRs, SBRs, various other types of variations on all of those. Some of them have special control systems built into them, powdered activated carbon, and so on. So these are all different types of unit processes, and they cover, hopefully most of anything that you could ever possibly see at a wastewater treatment plant. Certainly, if you have something unique, we can often take a couple of these things and combine them together to get what you need. For my little plant that I'm going to build today, I'm just going to grab a very simple plug flow activated sludge basin and put that down right there. We also have all of our biofilm models for the biofilm attached growth type processes. Trickling filters, BAFs, biological filters, rotating contactors, submerged contactors. And this last one down here is called the hybrid. That is used for doing any combination of suspended growth and attached growth together in the same tank. So this is what you would use if you were doing a moving bed bioreactor or an IFAS type reactor, where you're going to have some sort of media in place in the tank and along with the mixed liquor. And so I'll just mention very briefly that we did a very lengthy webinar on this actually a month ago, and that's available. If you want to go to our YouTube channel, you can see me talking in detail about how our biofilm models work and how you would use that particular unit. All right, carrying on now to the clarifiers, settlers, and so on. We have various shapes and sizes that you can see here. The light green ones are our primary clarifiers, circular and rectangular. And we also have the blue ones here that are for secondaries. So I'm going to grab, while I'm here, a secondary clarifier and put that down on the board. I'll also mention there's a few other different types of tertiary treatments here. These are upflow and downflow denitrification filters. We also have sand filters, membrane filters, disinfection units, and so on. So these are all there basically to allow you to sort of fill out the full treatment part of your plant. We also have the ability to model the solids handling line here with DAFs and thickeners and dewatering units of various kinds. There are some sort of generic things in here for doing basically any sort of solid separation that you like. And then we have digesters, of course, for aerobic and anaerobic systems. If you move on to our more detailed, our more complex model libraries, you'll see a few other units show up in here. We have a UASB, for example, and a struvite recovery system that would show up here in this side stream treatment. And then lastly, we have our tools area. This is really just kind of the hodgepodge of everything else. Black box models where you can build your own models to represent different types of technology. Our modeling toolbox, which is a collection of small tools that you can use to do control of your plant if you have a timer where something turns on and off and so on. And then our discharge unit, which is there really just to sort of signify the end of the system. Okay, so what I've done is I've built my little plant here. So all it is just activated sludge and a secondary clarifier. So up here, I'm going to pop up our little zoom window. I'm just going to zoom in on that nice and close so we can see what we're doing. And I'm going to connect these units together like this. You just basically do drag from one connection point to another. So here's our RAS line coming back around. And for each one of these unit processes, the next step would be to enter in all of the physical characteristics about how big these units are, how deep are they, what's their volume and surface area, and so on. And you do that by right-clicking in the middle of the object, and then this brings up the menus that you can use. So here in the input parameters menu, we would specify, for example, the physical volume of this tank, also how many reactors in series it is, and the depth, and so on. You can work in any kind of units that you like here by just pulling down the units menu. You can make little notes here if you want to type in anything that you may want to record while you're going through the process of this. Is very handy actually. If you're going to be working on this over a long period of time, you may come back and forgotten why you used a particular value. You can always see that value just by putting your cursor here. And typically you would also visit the operational menu. So this is basically after you defined how big that object is or what its physical characteristics are. Now you're going to say how it's being operated. And for this activated sludge unit, that basically boils down to any internal recycles, that kind of BNR setup, and most importantly, how it's being aerated. So you can see here we can pick between diffused air, mechanical surface aeration, we can have DO controllers on, or we can enter in a fixed airflow, which is what I'm going to do today. And I'm going to put in a little bit more air than what is shown by default there. So you'll notice when I change things away from the default, it highlights those in color. And there's all sorts of other details down here. If I clicked on this diffused aeration here, we could enter in all sorts of stuff about oxygen transfer efficiency and alpha and the saturation of oxygen under certain conditions and so on. Lots of detail in there. I also have recently done a aeration webinar, which you can go back and check out as well. Okay, so we've accepted all of those changes. We would do the same thing for the clarifier and so on. And once that's ready, we can go over here to simulation mode. Just for a quick blurb on the meaning of modeling and simulation here. Modeling is really the process of creating a model. So this is basically saying in that mode where I was dragging the objects around the screen, that was referring to building a model, which is modeling. Simulation is basically running the model. So in simulation mode, you can't make any changes to these objects down here right now. You would need to go back to where you could see the weight drawing board. So when you're in this mode here, everything is fixed, but now it's all about being able to run the simulation and get some results. So our model is actually finished here. You may have seen that screen pop up there for a few seconds. That was actually the Fortran compiler. In GPSX, what we do is all of our equations are written and we compile them externally in Fortran, mostly just because of the fact that it's much faster. It's there because of the speed. And it also allows us to include any other customization that we would like to do. We do have the ability to change the equations, to edit them, and add new equations along the way if you like. Okay, so the key things that we need to do here now before we run our simulation is provide some input, things for us to be able to play around with. And in this case, I'm going to right-click here and go to the Flow menu, and I'm going to grab the flow here and drag it up onto this panel. This gives me a little tool now, we call them sliders, where you can make adjustments to the parameters nice and easily by having that up there. And I'm also going to display some output on the right-hand side here. And the very easiest way to do that in the GPSX is just double-click on an object. You're going to get a large table with summary of the results of the most important things for you to know for this particular object. And I'm going to do one for the clarifier as well. And then at this point, if we wanted to do very simple, straightforward modeling, we would just hit Start down here in the left-hand corner, and we can see right away that we would get some results. So this is showing our mixed liquor in the 4 reactors here of 3,800. We can see that our DO is sort of depressed at the front end and up to about 3.6 at the back. And our ammonia goes down, nitrate goes up. So this is a nitrifying plant under these default conditions that I've provided here. So that's the very quick way to get all the results out of your model. But you can dig down deeper and get at some more interesting results by creating ourselves a new tab here, which I did up there. And I'm going to plot some of the profiles within this reactor. And I'm going to grab the dissolved oxygen, the soluble P, the ammonia, and let's grab the nitrate as well. And I just drag those over here. It makes graphs for me as I do that. We have a button here to sort of arrange all of those nicely. And if I press Start again, I get these types of bar graphs. This is the concentrations starting at the front of the tank. This is at the left here, and proceeding down the tank as we go here. So we can see our dissolved oxygen is very low at the front end of the tank. And as I mentioned, at the back end here, it's up to about 3.6. That was because I was just evenly aerating all the way down the length of the tank, of course. So our ammonia is going down here. We're generating nitrate and so on. So that's a very nice way to be able to get out some immediate results. And you could change the flow rate. We can increase the flow a little bit, rerun those results, and wow, we seem to have lost some nitrification here. So we were already pretty close on the edge, it seems. And we can also plot some results from the effluent here that will allow us to evaluate how things are going to change dynamically over time. So I'm going to plot TSS and BOD and TKN on a time series graph this time. And now I'm going to actually run 60 days of simulation here. And what I'm going to do is, I'll tell you ahead before it happens, I'm going to run 60 days. And while that 60 days is happening, I'm going to pop up here, grab this knob, and increase the flow for a little while, and then decrease it again so that we can see what's happening in this plant when we have an increase in flow over time. So I'm going to increase that for a little while, and then I'm going to bring it back again. I maybe go down a little bit below where we were previously and move that around a bit, and then let this run out for the remainder of the 60 days. So what's happening here is that we've now done a dynamic simulation. We started with the steady state answer that we have before, and then now I put in a couple of, well, you know, you could sort of consider these extreme wet weather events here, where we can see the solids increased quite a lot when I had the flow, and we lost nitrification there for a little bit, and then it came back again. So these are the types of analysis that you can do in a dynamic sense to get really interesting information out of that plant. So lastly, I'll say here is, how do I get all this stuff out of GPSX? And the way you do that is with a report function. We have several different places where you can get at this, but I'm going to use the report button up here, and I'm going to generate that. It's going to create an Excel spreadsheet for me, and I'm going to open that up right now, and you'll see here that what it does is it creates an Excel spreadsheet with tabs for each of the importance of what we've done. So here's the diagram that we had created at the beginning. Each one of these graphs that we created, here's the DO graph, has the image as it was at the end of the simulation, and a lot of the data that was used during the simulation down below. So we can see the tables of data. So therefore you could even make your own graphs if you like. So we have those for all the different parameters, and then we also have it for the tables that we created earlier. And then for each of the objects that we have in our layout, actually all of the input and output for each object is shown in these tables down here below. So that's a nice way to sort of summarize. This is a complete dump of actually all of the information from the model out for your access here that you can use to graph and include in your reports as needed. So that's kind of a nice, straightforward way of building a model, running a simulation, getting those results out. Okay, so I'm going to pop back to slides at this point and kind of wind things up as we get to the end of our time here. There are a number of things that you could try if you want to do this for yourself, just sort of taking it from where I've left it off here at the end of the first tutorial. One common thing that people like to do is when you're doing an evaluation side by side, it's sort of build the plant as it exists now, and then copy that plant and make another one side by side in the same layout, and then make whatever changes you that you want to make to that other plant, and then build that model. And so you actually have two plants running side by side. They can have the same input. And then you can see what the differences in the effluent quality is like sort of right beside each other. It's kind of a nice way to do things. You can use a dynamic file input controller to read a data for a wet weather event and then have that drive the model going forward. So I was just showing you where you can use the mouse to move the knob on that slider up and down in order to show how some flow increases over a period of time. You can actually make a spreadsheet that would have that, and it would take control and it would move that for you so that the flow went up and down automatically on its own. GPSX has a number of control loop options. You can try out some SRT controllers, mixed liquor controllers, sludge blanket height controllers, whatever it is that you want to be able to build, and test different strategy for taking things on and offline. These kind of match up with some of the things that I mentioned earlier that are the most common uses of our software.